This video is going to cover how to fill in your logbook. So the quality of your note-taking is going to count for half your lab grade every week, so it's worthwhile getting a good grip on what goes into the logbook in order to get full marks. I'm going to be going through two examples in this video, so you're going to see some concrete examples of what your logbook should look like. Now what you're looking at right here is page 4 of your lab manual. This bullet list here covers other things you need to do in order to get full marks. So I find it's helpful when you're looking through these to remember that your logbook is a legal document. It's admissible in a court of law. You could use it, for example, to prove that someone was trying to steal your patent. So in order for it to be admissible as a legal document, there's a couple of things that need to be true. So first of all, you need to write in permanent ink, and you can't obliterate any information from your logbooks. You can't erase something, you can't use whiteout, you can't tear pages out, and if you make an error, you should just put a single line through it and write the correction nearby. The point being that both the error and the correction are readable. We also want you to use a black hardcover lab notebook like you can get from the bookstore. The reason why we want you to get those ones is if it's got a glue binding or a staple binding, then it's clear that no pages have been removed. If you were using a spiral bound notebook, then you could tear pages out and no one would know. So we do want you to use the glue binding ones. Down here, do not remove pages from your notebook. We want you to sign and date every page. Initials are also okay, and you'll also need to record the time regularly as you work. I'm going to discuss those more when I go over the example logbooks. When you use symbols, make sure you define them, and when you take measurements, always write down the units and some uncertainty. So now I'm going to go through the two examples. In the first example, the jewel thief circuit, the experiment mostly consists of building a circuit and getting it to work. In the second example, for the Morse decoder, the experiment is mainly getting a piece of code to work. So you're going to see an example of how to write good notes when you're building equipment and how to take good notes when you're coding. Okay, so this is based on the jewel thief circuit. A jewel thief is a circuit that allows you to draw the last little bit of energy out of a battery that's nearly gone dead. You're going to have access to this document. It should be on the website. Now I'll just scroll back to this first page here. You should read over this at your leisure at some point. The only thing I'm going to note is that you do not need your logbook to look exactly like the logbooks that I'm about to show you. What we really care about is that you are recording the level of detail that we want you to. So I've had students where their logbooks looked like a long-form essay on every single page, and I've had other students where their logbooks looked like a bullet list on every single page. So you can organize your data however makes sense to you. We're pretty flexible about what we'll accept as long as all the information is there. That said, what I'm about to show you is a pretty good example of a logbook, so you can use this as a template if you want to, but feel free to change things as you need. So first of all, we require you to sign and date every single page. So I recommend that as soon as you turn to a new page, you sign it and date it, and you also write down the time. When your course instructor first started doing this course, he said to us, if they're not signing and dating every page, give them a 0. He wanted us to be that harsh about it. And the time was another thing where he said, if they're not writing down the time regularly, give them 0 on their logbooks. So these are things we require you to do to avoid those automatic zeros. So as soon as you turn to a new page, sign and date it. Initials are also fine, and then write down the time. You should actually write down the time several times per page, but once per page is the absolute minimum. You will lose marks if you don't do that. So when you start on a new experiment, start on a fresh page, write down the title, and it's a good idea to also write down an equipment list and also any programs that you used. Now this student has written down an objective for the whole experiment. You can do that, but what you might find more useful is to write down a task list. So when you get to the manual and it says do this, this, and this, just make a little task list, like a mini objective saying I'm going to do this, this, and this. It can be a bullet list, for example. Scrolling down, the next thing the student does is they're taking notes. So this is pretty common, is that you'll get to the experiment, and the first part of the lab manual will just consist of a bunch of theory that you need to read before you start actually doing anything. So your logbook is supposed to be a self-contained document. That means you're not supposed to refer to your lab manual at any point. If something's important, put it into your notebook. And a very easy way to do that is just as you're reading through the theory section, take notes. So whatever you think is important, you write it down. So that's what most of this page is as well, is just a bunch of notes, but again, notice that they sign and date every page and they write down the time regularly, even while they're just taking notes. Now down here we actually get to where they're starting to begin the experiment. So I want to pause here and just explain to you why it is that we insist you sign and date every page and write down the time regularly. So signing and dating the page, remember that your logbook is a legal document. This is just you attesting to the fact that you did this work on this day. Writing down the time, however, is a more practical matter. If you start doing this now, then by the time you graduate you will have developed a really good feel for how long it takes you to do certain tasks. And that's good for both you and your future boss in that you'll be able to make accurate estimates on how long it will take you to complete a certain project. Writing down the time is also good in the case where you're working on several projects at once because you can, after the fact, then bill your clients accurately for how much time you actually spent on their project. So that's why we insist that you sign and date every page and that you write down the time regularly. Now scrolling down here to where they're actually beginning to work on the jewel thief circuit. As it says here, your lab write-up should be so self-contained that an educated person could reproduce the experiment based just on your notes with no lab manual. So think about that. If you walked into the lab without a lab manual and I handed you a logbook from last year and said, do the experiment based on this, how much detail would that person have had to include it in order for you to reproduce their experiment? That's the level of detail that you should be aiming for as well. And for that reason, anything that's important needs to go in your logbook. So right here, they've actually drawn the jewel thief circuit from their lab manual. You can't just say refer to lab manual. If it's important, it needs to be in here. You copy it in. Down here, they've made a little error and they crossed it out with a single line and then wrote the correction nearby. And that's exactly the way to handle it. Just cross it out with a straight line, continue on. So coming down here, this is where they're actually starting to build the jewel thief. And you should be thinking of your logbook as a real-time diary. The idea here is that you do something, you jot down a note about it. You do something else, you jot down a note. So starting to build the voltage divider, they jot down a note, write down the time. Finished building it, jot down the note, jot down the time. And they just do that all the way through the experiment. The reason why you need to record this level of detail is that the biggest lie we tell ourselves is, I can remember that without writing it down. It's never true, or at least it's not true enough. And certainly in an exacting profession like engineering, you need all of that detail, and you simply will not remember it later. So that's why you have to write things down as you go along. So as I said, think of it as a real-time diary. You do something, you jot down a note about it. You do something else, you jot down a note. It's very human to want to just work until it's finished and then write it all up later. But that's exactly the habit we need you to break, because you simply can't remember enough detail later. It's quite annoying when you're first learning to do this to stop at every step and write down a note, but that's exactly the habit you're trying to develop in this course. And the real purpose for us writing down all of this detail is that it's not to benefit some hypothetical stranger who might want to reproduce our experiment. It's to benefit you. The idea here is you never have to re-engineer a solution if you took good notes. So for example, say you came up against some problem in the first week's lab. And say a couple of weeks later you come up against that same problem. You don't have to remember what you did, you can just go look it up as long as you took good notes. So this is why we want you to strive to include so much detail, is it saves you time in the long run. You never have to re-engineer something that you already solved. So getting back to the experiment, they say they're starting to build the jewel thief, and the first thing they're going to build is the voltage divider. So they do a little circuit diagram, and down here you notice they've got a very simple calculation. I do recommend that anytime you've got a calculation, even if it's something dead simple like this, that you actually write it all out. And that just goes back to having a complete record of this. You could come back 5 years from now and know exactly how you got this value. So this is just a very readable way to include all of your detail. Down here, this is a good technique. They say starting to build the voltage divider, they make a note of that, they write down the time. Then they say finished building it, and they write down the time again. So it's a good practice to record the time when you start and when you stop something. And if something's not going well and you have to keep troubleshooting, write down the time regularly as you're doing that also. So scrolling down a little more, they make notes to themselves about anything they find relevant. And next she says, okay, now I'm building the inductor coil. It's okay to write down references in your book, but remember, if something's important, it needs to go in the logbook too. So that's what they did here, is they included a reference, but then they wrote down the important stuff here also. And again, starting to build the inductor, writes down the time, finishes building it, writes down the time again, begins building the jewel thief circuit, writes down the time, finishes building it, writes down the time again, and notice she says it doesn't work. Now, it's never enough to say something works or doesn't work. You need to explain what led you to that conclusion. So you need to describe your observations. So immediately underneath, she says the LED only lights up at 5 volts and it's supposed to light up at a whole bunch of lower voltages. So she knows something's not working and she makes a record of that too. So next, she starts troubleshooting her circuit. Troubleshooting is a very important skill to acquire. The idea here is that you want to check things one at a time to try and find the one thing, hopefully, that isn't working. So she's just going through methodically and checking each thing in her circuit. So she first of all notes that the LED was turning on, so she knows it's not burnt out. Next, she double checks her wiring. Looks fine to her. She writes down the time. Next, she checks her resistor with an ohm meter, makes sure that it's about the right value, writes down the time. So after every step, she writes down the time. Next, she uses a voltmeter to check that her voltage dividers are working correctly, and when you've got lots of data like this, it's a good idea to make a table the way she has, and label it with the full quantity name, the units, and also the uncertainties. A title would also have been nice here. So she finishes up that, writes down the time, and this is also a good trick, is if you suspect some circuit element is burnt out, not working, first check that your wiring is not bad so that you don't burn out a second component. But a very handy way to check your hardware is simply switch out that component with somebody else's and see whether you see the same behavior. So if a different transistor fixed her problem, she'd know, okay, the transistor was the problem. And if it doesn't, she knows it's something else. Now here, if you ask somebody for help, whether it's another student or the lab instructor, write down their name. In the sciences and in engineering, we always want to give fair attribution to people who helped us, and also you maybe want to talk to this person again, so it's useful to write down their name just so you know who the expert was. Scrolling down, she's checking the next thing. She checks the voltages on the LED, and because there's a lot of them, again, she makes herself a table, full quantity name, the units, and the uncertainties. Down here, she notes that she did something wrong. She actually burnt out her LED because she hooked it up to too high a voltage. So the temptation is that when things are not going right, you just fix them and then you write it up. Again, that's a habit you need to break. When things are going right, when things are going wrong, it doesn't matter. If you did something, you jot down a note about it. So here, even though she screwed up, she still jots down a note about what happened and what she observed. Down here, she's saying that she has figured out what the problem is. These voltages up here for the LED are too low to turn it on. So now she needs to figure out what's going on, and she goes and asks the lab instructor, and again, she gives the name of the person she asked for help. Now before we get to that, we're first going to look at these oscilloscope traces. Now you're not going to be working with oscilloscopes for a couple of weeks yet, but this just gives you a good idea of the level of detail that you would need to record in your book when you do start working with the oscilloscope. So first of all, some sort of quasi-artistic squiggle is never going to be enough. You want an accurate transcription of what you saw on the screen. So first of all, make sure you give it a nice informative title. And you want to put your axes for the graph on there and label them. So you put the scale of the oscilloscope on both axes. Make one block of the graph equal to one block on the oscilloscope screen, and it may be hard to see, but the student has actually put dots on here to show exactly where the trace went on her screen, and then she joined them all up. So the point here is that if somebody was trying to reproduce your experiment, they could look at their oscilloscope screen and look at your transcription of what you saw and check whether they're seeing exactly the same thing you did. So that wouldn't be possible if you just sort of drew a wave shape in your book. You need to accurately transcribe what you see on the screen. Now fortunately for you, the oscilloscopes that you're going to be using actually allow you to capture the image on the screen, save it to your flash drive, and then print it out. So you probably won't need to do this by hand. But regardless of whether you're capturing the image or drawing it in, you need this level of detail in your book when you're recording what you saw on an oscilloscope. So here's where we see the student actually making that oscilloscope trace you just looked at. She says, okay, she's setting up the oscilloscope, writes down the time. Finished setting it up, writes down the time again. Now she's sketching what she saw, writes down the time. Finished sketch, she did write down the time. I've covered it up here. And she comments on what she's seen. In this case, it was the flat line that you saw at the top of the previous page. So she asks the lab instructor for more help because she knows that's not right, and they finally figure out what the problem was. She had two wires swapped. And then she says, great, it works now. But remember, it's not enough to say something worked or didn't work. You need to explain what behavior you saw that led you to that conclusion. So she explains the LED lights up visibly for all of these different voltages, but not for this one, which is what she expected to see. So she draws her second oscilloscope trace here. Next, she's going to start analyzing what she saw a little bit. Now again, she's got some simple calculations, but she writes out all of the steps so that if she comes back to this even years later, she knows exactly how she got these values. Down here, these are the sort of quasi-artistic squiggles that I say are not really adequate in your logbook, but because she did a full oscilloscope trace and actually drew it out properly, this would be acceptable. But generally speaking, if you just draw little squiggles like this, you definitely are going to lose marks for that. And down here, there was a question in the lab manual, so she answers it here, and she makes sure to include enough detail that somebody reading through this without the lab manual on hand can understand what she was talking about. And then she's finished. Now, you don't need to write a separate conclusion for your experiments, but it's a good idea to write sort of a mini conclusion, and that's exactly what the student did way back here when she explained what she saw. So this is where she says the LED is now lighting up for the appropriate voltages. This is her conclusion, and that's all she needs. So this is the second of the example logbooks. This is for the Morse decoder. So the idea is that this is a little circuit where she's got a button and she pushes the button in Morse code, and then the program actually decodes that for her. So to begin with, she signs and dates every page. She writes down the title, and here she's got an equipment list and also a list of all the files that she used, because this is a project that has a lot of coding in it. Then she starts reading the lab manual. It's obviously got some theory because she's taking notes, and she writes down the time when she begins and when she finishes. And down here, she's gotten a little more efficient. Instead of writing an objective, she's written a task list. Again, signs and dates every page, keeps track of the time as she goes along. Now here she's noting that she can reuse some circuitry that she already had set up on her breadboard, and she's also going to be reusing a bit of old code, which is pretty common in this course. Now down here she says she's creating a project in the Mplab program. You're going to be doing this pretty much every single week, if not several times a week. So she's written a nice concise summary of how you actually go about creating a project. She puts down all the different steps. But like I said, you're going to be doing this pretty much every single week. So something you might consider doing is take all of these steps and put them in the back of your logbook as an appendix. And then you can just say, created a project, see appendix on the last page of this logbook. So that would save you a bit of writing. So coming down here a little bit, and she says she's creating a file called morsedecoder.c from a supplied file called morsedecoder.txt. So this is something that was provided to her, and she's changing it. Now, the way the student handles making changes to this existing code is she just makes notes in her logbook. Another way to handle this, you don't have to, but another way some students do this, is they'll take that old code, they'll print it out, they'll paste it into their book, and then they'll make changes. So they'll annotate it. They'll change things by hand and just, use arrows and little notes saying what they changed. If you do that, make sure that you write down the time, because when you're finished, you'll have this piece of code with arrows and little notes and all the margins, and it won't be in chronological order. So you need to write down the time every time you write down a comment. So you can do that, or you can do what she does, which is every time you make a change in your code, you just write it down by hand in your logbook. So in what comes next, what you're going to see is a combination of her taking good notes about what she's doing, but also this is interspersed with her actually planning what she's going to be doing. So right now she's just planning that she's going to change a function she's already got. Here she notes some stuff she learned in a previous lab, does her calculations so that she knows what she needs to do in this week's experiment. And coming down here, she actually starts changing her code. So she says she copies and pasted some commands into this new file, and she changes a prescaler. And down here again, she's saying, okay, I add this line, I add this line. So again, as before, the tendency is for you to want to just keep working on it until it works and then write it up. You can't do that. That's the habit you need to break. Every time you do something, you need to write down a note about it, and that includes when you're coding. So she changes a line, she writes down a note. She changes another line, she writes down a note. That's how you should handle it. So think of your logbook as a real-time diary of what you're doing as you do it. Here, she's thinking a little bit more about what she needs to do. She writes a bit of pseudocode, and then she is making a note that she has added this to her code. And here, continuing on, she's just taking really good notes about what she did as she did it. So added a line, added another line, added another line. So everything she changes, she makes a note about it. This carries on for quite a while, so I'm going to skim down to the point where things start going wrong for her. And that's about here. So what happens is at this point she has built her circuit, she has finished creating her code, and now she's going to try and build it and see whether or not the project builds. And it doesn't. She gets a warning message. And so again, remember, the tendency is when things go wrong, you just want to fix it and then write it up later. That's a habit you need to break. Whether things are going right, whether things are going wrong, always take notes as you go along. So the way in which you handle that is you write down the warning message, including its number, and the message that came with it, and then when you find a solution, write down that as well. So that's what she did. And she gets a build failed. Again, she writes down the full warning, including the number, and here she's saying it happened 12 times, so she got a whole bunch of warnings here. She figures out what the problem was, and she outlines how she fixed it. So again, a nice concise summary of how she actually fixed that one setting. And as this keeps happening, as she keeps getting these build faileds, she starts writing in the time. And so she just keeps doing this for as long as it takes to get things to actually work. And finally, right here, this is where they do work. Build succeeded, no errors or warnings. So she programs her target device. But then she discovers something else has gone wrong. The program isn't working the way she intended. Remember, it's not enough to say something worked or didn't work. You have to explain what you saw that led you to that conclusion. So she explains. Nothing shows up on the screen. So now she has to start troubleshooting. So first of all, she knows her LCD is working, so she starts using some of the debugging tools, which you guys are going to learn about in a few weeks. So she puts in some breakpoints and steps through her code, and here's an observation, and it winds up being the thing that actually helps fix the problem. So she figures out what this means, she makes her fixes down here, takes good notes on all of those, gets a build failed, fixes that, build succeeded, no errors, program the target device. And now it looks like it's working. So remember, you have to say why you think it's working. So she explains. 5 taps of the button gives what looks like a correct display. So then she starts testing things, and again takes really good notes, and in doing so she actually finds that things are not working correctly. Some of the numbers are the way they're supposed to be, and some of them are not. So she has to do some more troubleshooting. So she thinks about it, tests a little bit, figures out what the problem is. Fixes it. Tests it again takes good notes on what her results are, and this time it's working. And again, at the end, it's probably a good idea to put in sort of a mini conclusion, which is just usually, it works, and this is what I saw. So she says it works as intended, and explains what she saw that led her to that conclusion. Now remember that your logbook is supposed to be so complete that a stranger could take it and reproduce the experiment. They would need your code in order to do that, right? So you always want to attach your code to your logbook. So down here, she's done that. There's quite a bit of code, so it's a good idea when you've got a big chunk of paper to add to your logbook to fold it in half and then staple one edge to a page of your logbook so that you can fold it open and have a look at it. But you would include all of the code, and it's important to also include enough comments that somebody could look at your code and read just the comments and understand how your code works. So it's very common to forget to put in enough comments. So before you print out, it's a good idea to just double check whether you've got enough comments.